In section 5.6, we're going to now put together all the information that we learned in chapter 5, and we're going to graph functions using the following procedure. So number one, we're going to analyze the first derivative. By doing that, we're going to perform the first derivative test. We're then going to determine from that test what our critical numbers are, where the curve is increasing and decreasing, and whether or not the curve has any relative max-min points or relative extrema. We'll then turn our attention to the second derivative telling us about the concavity of the function. We're going to add some fine-tuning to the graph by calculating the x and y intercepts. If the function happens to be a rational function, then we'll also study the asymptotes. And finally, we're going to just take all that information that we've got and draw a picture of the graph. So what I'm going to do for you now is I'm going to take you through three functions, and we're going to graph them in their entirety following this procedure. And the three functions that we're going to do will be the functions that you're responsible for. I'm going to do a polynomial function, a rational function, and an algebraic function, one involving radical signs. For our first example, we're going to look at what's called a polynomial function. This is a degree 4 polynomial function, and ultimately the goal of this chapter is for you to draw a picture of this graph by analyzing its derivatives. So what we're going to do is we're going to follow the procedure that I just mentioned. So step one, in step one we're going to analyze the first derivative. So what we'll begin doing is we'll take the derivative f prime. Since this is a polynomial function, we're just going to use our power rule. So this will be 4x cubed plus 12x squared. So remember that the first derivative gives you the slope of the tangent. So what we're interested in doing here is we want to know when is the slope positive, when is it negative, when is our curve rising, when is it falling. And so what you do is you start by making it equal to 0. So you turn your first derivative into an equation by making it equal to 0. To solve, you would take out a common factor of 4x squared times x plus 3 equals 0. And we end up with two critical values, x equals 0 and x equals negative 3. Critical values, if you recall, are any places where the derivative is 0 or where the derivative is undefined. So what we have here is 0 and negative 3, which means that those two places our curve has a horizontal tangent. So what we do now is we perform what's called the first derivative test. So if you recall, the way you perform the test is you set up a chart. You start at negative infinity, and you move to the right until you get to your first critical point, which would be negative 3. Then you indicate your critical point, and then you'd go from negative 3 to your next critical point, and then 0, and then all the way to plus infinity. And what we're trying to do in this test is we're trying to determine when is the derivative positive and when is it negative. So underneath the negative 3 and the 0, we're going to put zeros, because that's how we found our first derivative. If you were to plug negative 3 and 0 into your first derivative, you would get 0 for an answer. Now what we do is call the sign analysis. And if you recall, the way to do this is, especially if you have your derivative in its factored form, it's simply analyzing the signs. You're not using a calculator. So if I was to pick something in the interval negative infinity to negative 3, for example, if I was to pick negative 4, if I put negative 4 into my first derivative, 4x squared will always be positive. Negative 4 plus 3 is negative. So I get a negative times a positive, so my first derivative is negative. Now if I do that, continuing on in my test, pick something between negative 3 and 0. So let's say I pick negative 2. This is positive. These are the little shortcuts you can pick up on. Because this is being squared, I can basically ignore that part of the derivative. Really all I'm testing is the x plus 3. So if I plug in something like negative 2 plus 3 would be positive. And something between 0 and infinity, so let's say we picked 1. 1 plus 3 is positive as well. So we've just finished our first derivative test. And from that test, we know that the negative indicates the curve is falling. 0 means it's flat. Positive means rising. 0 means flat. And positive means rising. So we would say that our curve is increasing from negative 3 to 0, union 0 to infinity. and our curve is decreasing from negative infinity to negative 3. We can also tell from this first derivative test whether our curve has any relative extrema. You'll notice at this point right here, the curve was falling and then rising, so this is going to be a local or relative minimum value. And the curve never does have a relative max. This is not a max here because this would have to be negative. So we would say that our curve has a relative min value at 0. Now you need the y value, so you plug, and I'm sorry, that's not 0. My mistake. That's negative 3. So there's a relative min at negative 3. So you take negative 3 and you plug it into the original function. So negative 3 to the 4th plus 4 times negative 3 cubed, and that turns out to be negative 27. So at that point, our curve has a relative min, and relative max, there are none. That takes care of the first derivative. So from the first derivative, we can tell the critical values, we can perform the test, and we can tell our intervals of increase and decrease and our relative extrema. So we now turn our attention to the second derivative. With polynomial functions, the second derivative just is even easier than the first derivative because every time you take a derivative, the degree gets smaller. So the second derivative, f double prime, we're going to take our second derivative of our first derivative. So we're going to get 12x squared plus 24x. We're going to make it equal to 0, take out a common factor of 12x, and we find critical values at 0 and negative 2. We now perform the exact test we performed with the first derivative, except this time we perform the second derivative. And just a point of note here, this is not called the second derivative test, this is called the concavity test. It would be negative infinity to negative 2, negative 2, negative 2 to 0, 0, and 0 to infinity. These are both 0. We perform this test exactly the same way we did the first derivative test. We plug numbers in our open interval into our second derivative in its factored form. Notice that this time this is not squared, so we have to be sure to test both factors. So if I pick negative 3, 12 times negative 3 is a negative number. Negative 3 plus 2 is a negative number, so I'm going to get a negative times a negative, which is a positive. If I pick negative 1, this will be negative, this will be positive, which will be negative. Once you get the hang of these tests, they go quite quickly. Notice that I'm not using a calculator. 0 to infinity, I'll pick, and again, it doesn't matter what you pick in this interval. I could pick 10. 12 times 10 is a positive number, 10 plus 2 is a positive number, and so our concavity test is complete. From this test, we can tell the concavity of the function. So we would say that our curve is concave up whenever it has a positive second derivative. So it's concave up from negative infinity to negative 2, union 0 to infinity. It's concave down from negative 2 to 0. And inflection points are any points where the concavity changes, which would be at negative 2 and also at 0. To calculate the y values, you just plug in your x values into the original function. So it would be negative 2 to the 4th plus 4 times negative 2 cubed. And that turns out to be negative 16. And if we plug 0 in, we get 0. The next thing we're going to do is calculate the intercepts. So we're going to calculate the x and y intercepts. So what we do there is we take our original function, f of x, and define the x-intercepts. We put 0 in for y. So 0 equals, and if you're going to find x-intercepts, you have to factor. So this is going to be x cubed times x plus 4. So the x-intercepts are going to be 0 and negative 4. So our graph is crossing the x-axis twice. And the y-intercepts, remember that there can only be one y-intercept. So if your x-intercept is 0, which is the origin, it must also be your y-intercept. If you plug 0 in for x, you could verify that. Step 4 is study the asymptotes. Well, there are no asymptotes in a polynomial function, so that step is not relevant. And all that leaves now is for us to put all this information together and draw a picture. So I've drawn myself a coordinate plane, and what I want to do now is I want to graph the function x to the fourth plus 4x cubed. So what I would do first of all is start by marking off all my intercepts and all my critical points. So we need a scale, so we can just mark off some units here. If you recall the x-intercepts, the graph crossed the x-axis at -4 and 0, and the y-intercept was also 0. Critical values, if you go back and look at your tests, there was a relative min at -3, -27. Now obviously that's quite far down here, so we don't need to draw that accurately. -3, -27, so down here somewhere our curve has a relative min. There was also an inflection point at -2, -16. So somewhere in here there was an inflection point, and there was also an inflection point at 0. If you put all the pieces together, the curve started by falling and concave up. So it's going to come down like this till it gets to here. At this point it became an increasing function, but it was still concave up. So it's concave up until here, in which case it inflected and became concave down, but it was still rising all the way to 0. At 0, the curve changed, an inflection point again, and became concave up, and the curve also continued to rise. So it just turned around and went like that, and we have a fairly accurate picture of a polynomial function. Okay, the next function I want to look at is a rational function, f of x equals 2x over x minus 3. And again, our goal here is to graph this function following the procedure that we've already seen. So first of all, we're going to analyze the first derivative. So step 1, we need to find f prime. So we take the derivative f prime. What we have here is a quotient, a function divided by a function. So I'm going to use the quotient rule, which says take the derivative of the numerator times the denominator. Subtract the derivative of the denominator, which happens to be just 1, times the numerator, divided by the denominator squared. So there's my first derivative. Now we're going to have to find the critical points, if there are any, and we're also going to have to take a second derivative. So it's absolutely essential that we know how to simplify our first derivative. Now in this case there isn't much to do. We can distribute the 2 into the bracket, and we'll end up with f prime being 2x, take away 2x, which cancels. So we'll end up with just minus 6 over x minus 3 squared. So there's our first derivative in its absolutely simplest form. Our next step is to find any critical points. So what we do is we take the first derivative and we make it equal to 0. Now you'll notice that that has no solutions. When you have a fraction equal to 0, it has to be the numerator that's equal to 0. Negative 6 doesn't have a variable in it, so negative 6 can never be 0. It'll always be negative 6. If that doesn't make sense, you can put this over 1 and cross multiply. If you cross multiply, you'll end up with negative 6 equals 0, which is no solution. Therefore, our conclusion is there are no critical points. All that means is that there are no points on this graph where the tangent is horizontal. It doesn't mean that we still can't analyze the first derivative to see when it's increasing and decreasing. So what we do now is we perform our first derivative test. Your first derivative test can still be performed even though there are no critical points because we have a vertical asymptote. Wherever there's a vertical asymptote, a function can change its behavior. And so when you do your first derivative test, you include all vertical asymptotes and all critical points. Now in this case, we're just going to go negative infinity up until 3, which is our vertical asymptote, 3, and then 3 to infinity. Underneath the 3, if you plug 3 into the first derivative, it would be undefined. So we just put undefined here. And then what we do is we perform our test. Now, you'll notice that our first derivative is a negative number over something squared. So no matter what we plug in for x, the bottom will always be positive, and the top will always be negative. So what's happening here is regardless of what interval we're on, our first derivative is going to be negative and negative. So we would say that our function is decreasing from negative infinity to 3, union 3 to infinity, and increasing never. If you were walking on this graph from left to right, you'd never be walking uphill. And you'll see that once we get to the picture. Therefore, there are no relative extrema. Okay, so that finishes our first derivative analysis. So now we turn our attention to the second derivative. So the second step of our procedure, number 2, is we're going to analyze the second derivative. So to do that, we have to take the derivative of the first derivative. Now you'll notice that our first derivative is a quotient, but in this case the numerator is a constant. If you have a constant, you should never treat it like a function. We should not use the quotient rule here. What we should do is we should take our first derivative and rewrite it so that we have negative 6 times x minus 3 to the negative 2. If you were to use the quotient rule, it would work out, but it's much more efficient if you treat it like a constant times a function. If this was 6x, I would never move this to the top. I would use the quotient rule, but in this case, that's what I would do. So now when I take my second derivative, f double prime, this is not a product now, this is just a constant. So I have a constant times a function, and the function is being raised to a power. So I'm going to use my power rule. So I'm going to go negative 2 times negative 6, which is 12, times x minus 3, subtract 1 from the exponent, times the derivative of the inside of the function, of the power, which happens to just be 1. Making that into a simpler form, we end up with 12 over x minus 3 cubed, and that's our second derivative. You'll notice that if we make it equal to 0, we have the same situation as the first derivative. We have no critical points. Therefore, when we analyze our second derivative, our concavity, we're only going to use our asymptote again. So we now do the concavity test. The concavity test is performed the same way as the first derivative test, except we analyze the second derivative. So it's going to be negative infinity to 3, 3, and 3 to infinity. Once again, this is undefined. This time when we plug our numbers in our interval, you'll notice that the bottom is cubed, and therefore we can't just assume it's always positive. So if we plug in something from negative infinity to 3, for example, let's say we plug in 2, the top is always positive. The bottom would be 2 minus 3, which is negative cubed. So this is going to be negative. And if we plug in something bigger than 3, the bottom will become positive. And so we do have a concavity change at our asymptote. So our curve would be concave up whenever there's a positive second derivative. So concave up from 3 to infinity. Concave down from negative infinity to 3. And there are no inflection points. You'll notice that our curve does change concavity, but it doesn't change at a point. It changes at the asymptote. So there are no inflection points. Step 3 in our procedure. Step 3 is to find the intercepts. This is a fairly simple step. It's just meant to give us a little bit more information. To find the x-intercept, we just plug 0 in for y into our original function. So we're going to have 0 equals 2x over x minus 3. Cross multiplying, you'll notice again that it's only the numerator that matters. So we have 2x equals 0, so there's an x-intercept at 0. If the x-intercept is 0, then automatically we have the y-intercept because it's going through the origin. So in this case, the intercepts didn't give us too much information, but they did tell us that the graph was crossing through the origin. In step 4, we're going to analyze the asymptotes. The vertical asymptote in this case would be x equals 3. That's what would give us 0 in the denominator. So we do our limit statements. What's the limit as x approaches 3 from the right of the function? And what's the limit as x approaches 3 from the left? If you recall, to perform these tests, what you do is you pick something really close to 3 from the right-hand side, like 3.1, and you plug it into the original function. If you plug 3.1 in, the numerator will be positive and the denominator will be positive, so we know that the graph is going off to positive infinity. If you plug in something below 3, like 2.9, the numerator will stay positive, but the denominator will become negative, and so the graph is going off to negative infinity. At this point, step 5 is where you sketch your picture. For rational functions, I like to sketch my graph the moment I start analyzing the asymptotes. So I know that there's a vertical asymptote at 3. And coming in from the right, the graph is going up, and coming in from the left, the graph is heading down. I know it's going through the origin. I now turn my attention to the horizontal asymptotes. The horizontal asymptote, if you recall, can be found by multiplying by the largest degree of x. Or, if you know the shortcut, I would prefer if you just knew the shortcut. If the degrees are the same, x to the 1, x to the 1, the horizontal will just be at y equals the ratio of the leading coefficients, which in this case will be y equals 2. So we know that our graph has a horizontal asymptote right here at 2, and the rest of it is just finishing off the picture. Obviously the graph is coming down like this, coming up through the intercept like that. So we write our limit statements. The limit as x goes to infinity of our function. As we head off toward infinity, we're approaching 2, but we're approaching it from above, or the positive side. And the limit as x approaches negative infinity of our function is also 2, but this time we're approaching it from underneath. You'll notice that our graph, that our derivative tests make sense. The graph is always decreasing. So if you're on this graph, you're walking downhill. And then, of course, you jump over the asymptote, and then you continue to walk downhill. You'd never be walking uphill on this graph. But notice that there's a concavity change. The curve is concave down below, or to the left of the asymptote, and concave up to the right of the asymptote. So that's how you would graph a rational function. For our last example in this section, I'd like to look at a third type of function. This is an algebraic function that has radical signs. The function is x to the 2/3 plus 1/5 x to the 5/3. There's an interesting feature that happens in these graphs that doesn't happen in the previous examples I've done, so that's why I want to take you through one. So first of all, again, we do our first derivative analysis. So f prime of x. This is just a power rule. So our derivative would be 2/3 x to the negative 1/3 plus 1/3, multiply the 5/3 out front, x to the 2/3. Now we have to locate our critical point, so we're going to make that equal to 0. The key to solving these kind of derivatives is to take out a common factor. If I take out a common factor here of 1/3 x to the minus 1/3, if I remove that as a common factor, I'll end up with just 2 plus, when you remove a negative from a factor, it's like adding. So what you do is this would become x to the 3/3. The 1/3's coming out, so we end up with just 2 plus x equals 0. You can always verify that by just multiplying it back in. Think of this as being x to the 1. So if you add negative 1/3 and 3/3, you get x to the 2/3. I'm just going to rewrite this. This would be 2 plus x over 3 cube root x equals 0. Now recall, critical points occur wherever you have a derivative that doesn't exist, is undefined, but the point is still in the domain, and any point where the derivative is 0. Well, this derivative would be 0 at negative 2, so there's a critical point at negative 2. But notice that if you plug 0 in for x, that the derivative would not exist. But 0 is not an asymptote. 0 is part of the domain of the original function. This curve does exist at 0. So there's two critical points, one at negative 2, one at 0. What's happening in this case, when the derivative is equal to 0, your tangent is horizontal. In this case, the tangent is undefined, which means that you have a vertical tangent. But they're both critical points. They're both critical numbers. So now we perform our test. Our test is going to be from negative infinity to negative 2. That's our very first critical point. Negative 2, negative 2 to 0, 0, and 0 to infinity. This is 0. However, this one is not 0. This one's undefined. Same as if you had an asymptote, but in this case it's not an asymptote. Now to do the test, we just plug numbers from this interval into our first derivative. So if I pick something like negative 3, I get 2 plus negative 3, which is a negative. The cube root of negative 3 is a negative, so we end up with a negative over a negative, which is a positive. If I pick negative 1, this will be positive, but this will be negative, so I get a negative. And if I pick something bigger than 0, like 1, everything is going to be positive. So I would say that this curve is increasing from negative infinity to negative 2, union 0 to infinity. The curve is decreasing from negative 2 to 0. And local extrema, a positive derivative means rising, negative means falling. So this negative 2 right here, the negative 2 is a relative max. So we have a relative max at negative 2. We need the y value, so you take that negative 2 and plug it into the original function. You're going to get an irrational number, so in this case we would just round off. It works out to be about 0.95. And right here at 0 we have a min. Even though the tangent isn't horizontal, even though it's vertical, the curve is still falling and then rising. So we have a relative min at x equals 0. And if you plug 0 into the original function, you get 0, 0. Okay, so that takes care of our first derivative. So now we turn our attention to the second derivative. So step 2 in our procedure is to analyze the second derivative. So f double prime, we take the derivative of our first derivative. Now the question is, where do you do that? I would just use this form right here. Otherwise, if I use this one, I have to use a product rule, and this is a quotient rule. So I would just go right here and take my second derivative and get negative 2/9 x to the negative 4/3, subtract 1 from the exponent, plus 2/9 x to the negative 1/3. That's just using the power rule based on my first derivative. Now I need to do the same kind of math I did on my first derivative. I need to take out a common factor. So I'm going to take out a common factor of negative 2/9 x to the negative 4/3. That will leave me with just 1. This sign will change, and this will just become x. I can rewrite that as negative 2 times 1 minus x all over 9 times the cube root of x to the 4th. Make that equal to 0, and we got critical values at 1 and another critical value again at 0 because of the dividing by 0 in the second derivative. So now we do our concavity test. It's going to be negative infinity to 0, 0, 0 to 1, 1, and 1 to infinity. This will be undefined, and this will be 0. Picking something below 0, like negative 1, notice that the bottom is always positive. These are little shortcuts you want to pick up on that can save you a lot of time. Because this is x to the 4th, we basically can ignore that. And so all we have to do is plug negative 1 into our numerator. 1 take away negative 1 is a positive times a negative, so we get a negative value. 0 to 1, I'll pick a half. 1 minus a half is positive. A positive times a negative is negative as well. And something bigger than 1, like 2, 1 subtract 2 is negative, and negative times a negative is a positive. So our curve is concave down from negative infinity to 0, union 0 to 1, concave up from 1 to infinity, and inflection point. there's an inflection point wherever the concavity changes at a point. Well, that would be only at the point 1. So it's 1 comma, and I've already plugged it back into the original function. It turns out to be 6/5. The next step is to do our intercepts. To calculate our x-intercepts, we can just go 0 equals x to the 2/3 plus 1/5 x to the 5/3. Take out a common factor of x to the 2/3, and we get 1 plus 1/5 x. So we have x-intercepts at 0 and -5. The y-intercept is going to be 0 because the x-intercept is 0. There are no asymptotes, so step 4 in your procedure is to analyze the asymptotes. There are no asymptotes in this graph. The function exists for every value of x. And so finally we just draw a picture. So our picture, number 5, would be to sketch the graph. And our picture would look something like this. We've got x-intercepts at 0 and -5. We have critical values. We have a min, a min at 0, 0, and a max at -2 and almost 1. So -2 and up 1 is going to be a relative max. And there's an inflection point at 1, 6/5. So over 1 up about 6/5. And so our graph is coming up like this, concave down. Stays concave down here. So it turns around like that and starts to decrease. At this point, it switches concavity and becomes concave up. Sorry, I take that back. It's still concave down. It's concave down till 1. So still concave down like that. At this point, it switches and becomes concave up, but it's still rising. So the curve ends up turning around and going like that. You'll notice that there's a critical value right here that the tangent is horizontal. At this point right here, if I just magnify that for you, the graph is coming down like this and then like that. At this point, the tangent would actually be vertical. That's why the derivative was 0. Some people call that a cusp on the graph. Okay, so we've wrapped up this section. I've drawn 3 graphs for you. Those are the only types of functions you're responsible for, and you've now seen an example of each one.